All right. 10.2 is using the fundamental counting principle. This is going to help us find the number of ways to do certain tasks without actually having to list them all out. In 10.1, we didn't really have a good way to figure out the number of ways, that you could pick a president and a secretary and a treasurer from this number. We just kind of had to list them out. Yeah, we had the table method, and we had the list method, and we had the tree method, which were all different ways of getting the same thing. But what it came down to is we still had to list every single possibility. If we were rolling dice, we had to list every possibility for those dice. And we're going to see that there's a little bit of an easier way if it sticks to this uniformity criteria. So these two things are kind of important, and then we'll get to do a whole bunch of problems and see how this actually is applied. We're going to have a couple of different formulas of sorts so that we can simplify our tasks and not have to write out that there are 81 possibilities. I don't know about you, I don't want to list that out. Or one of our problems, we're going to have 17 million possibilities. Definitely don't want to do that. So we are going to learn how to not have to list everything. So the uniformity criteria says that a multiple part task is said to satisfy the uniformity criteria if the number of choices for any particular part is the same no matter which choices were selected for the previous parts. And so I included, actually it was the last problem that we did in 10.1. I just included the tree diagram for that. This is where we were making 3-digit numbers without repetition. And so for our first digit, we had 3 choices. For our second digit, no matter which one we started with, we had 2 choices. And for our third digit, we would only have 1 remaining. And so this works with our uniformity criteria. Every single digit has the same number of options, regardless of where we start. That's what the uniformity criteria says. And if we have that, then we get to use the fundamental counting principle, which makes our lives so much simpler. The fundamental counting principle states that when a task consists of k separate parts and satisfies that uniformity criterion, if the first part can be done in n1 ways, and the second part can be done in n2 ways, and so on until you hit the kth part, which can be done in nk ways, then the total number of ways for completing that task is n1 times n2 times n3, all the way through n times k. I know when it's in general, it can be a little bit confusing, and so it's easy to see up here with this first one. So for our first digit, how many different ways did we get to have? Like, what's the choices? How many choices did we have for our first digit? 2. First digit, that's this one. How many different options did we have for our first digit?
There's
3 different options, right? And then for our second digit, how many different options did each of those have? 2. And for our third digit, how many different options did each of those have? So what the fundamental counting principle states is that I can take the number of options for each of these and multiply them together to get the total number of possibilities. And I don't have to list out a single thing. Now, this one had a tree diagram, and so we could see all of the actual numbers. But in general, we won't have to know what the actual numbers are or what the actual elements are within the group or the set. All we're going to have to know is how many things can go first, how many things can go second, third, fourth, so on and so forth. And then we're going to multiply all those together, telling us the possibilities. What we're doing here is actually, if you ever go to Sonic and you see on their drink menu and it says that they have like 46 million different drink options, it's literally this. They compile their groups based on, okay, they can pick this soda, and they have this many options for the sodas, they have this many options for the things you can add to your soda, they have, all of that, and they multiply them together, and that's how they're getting that huge number, is by doing this fundamental counting principle. So what this saves us is we will no longer have to list all of our items. We don't have to find them out. We're just going to find the number of ways, which simplifies our life quite a bit. Because as I mentioned, our groups are going to get bigger. Our sets are getting bigger. The number of possibilities are going to be enormous. And we're not going to be listing all that. So for our fundamental counting principle, sometimes your problems will specifically state to use this. But the only thing that's required is it has to do the uniformity criterion. If I can pick this option and I have 3 choices here, and for this option I only have 1, then it's not uniform. It has to be consistent all the way through. But I do know your homework, and a lot of the problems will specify use the fundamental counting principle. And so that kind of directs you what we're going to do. Let me zoom out just a tick over here. All right, how many 2-digit numbers are there in our base 10 system of counting numbers? Hint, 40 is a number, is a 2-digit number, but 04 is not. Okay, we don't consider another number 4 a 2-digit counting number. Even if we put that 0 out there, it doesn't work. And so if it's 2 digits, then we're going to have our first digit and our second digit. And luckily, we don't have to sit here and write all of the 2-digit numbers between 10 and 99. We don't have to do that. What I have to think is how many first digits will I have? There will be 9 possible because we're not going to include 0 as a starting first digit. So we'll have 1, 2, 3, all the way through 9. So there's 9 possibilities here. How many possibilities do we have for our second? Exactly. We get to include 0 as a second digit. And so there are 10 second digits. So using the fundamental counting principle, I'm going to take 9 times 10, and I get 90 2-digit numbers. And hopefully that makes some logical sense if we know all of our numbers between 0 and 100. If we cut off the first 10, we're left with 90. But the next example makes it a little bit harder. Find the number of 2-digit numbers that do not contain repeated digits. So I can't have the number 11. I can't have the number 22. I can't have repeated digits, different D word. So we're still going to start with the first digit. How many possibilities are there in the first digit? There's still 9. We still get 1 through 9 in our first digit. So there's 9 choices here. Now our second digit requires us to think for a second. Before we had 10. We had 10 possible choices for our second digit. How many possible choices do you think we have now? Let's just look at one number. So if our starting digit is 1, because that'll be the first one that we encounter. So if our starting digit is 1, how many choices do we have for that second digit? 9. We have 9. Because we're going to take away the number 1 out of circulation, because we can't have the number 11. All the other numbers, 0 through 9, except for 1, works. And if I go to 2 as my starting number, all the numbers work in my second digit except for the number 2. So every single time I change my first digit, I still am going to have 9 choices. They're just different choices. And that's okay. I'm still going to have 9 different choices here. So I will have 9 times 9, which means there's 81 possibilities, or 81 2-digit numbers that do not have any repeating digits. What we did is we took out all the repeating digits from this. We took out 11, 22, 33, 44, and so on and so forth, which there's 9 of them. So the choices don't have to be the exact same in order for us to do this. Even up here, if 1 is my first digit, I have the options of 2 and 3 as my second digit. That's not the same if I had a starting digit of 2. It's not necessarily that my options are exactly the same. It's that I have the same number of options. That's what makes it uniform. Any questions or clarifications on these first two? right, let's look at some more. We're going to do lots of problems. We're going to look at that club N or group N that we talked about last time. It changes a little bit depending on the problem. This one did give us a picture, which isn't totally helpful. It's more helpful to know which of our students are male and female because that's relevant to this problem. It says, how many ways can our club N, which is A through E, elect a president and a secretary if no one may hold more than one office and the secretary has to be a man? So there's two different stipulations that's going on here. We're going to pick two different people to be two different positions. It cannot be the same person. And our secretary has to be a man. So luckily they list out who our men are. Our men are A, B, and D. Those are our men. Everybody's eligible for these positions except, I guess everybody's for A, B, C, D, and E. Those are all available for president. But for secretary, A, B, and D are our only options, is what it comes down to. So whenever we have multiple different things at play, multiple different limitations, put the most restrictive one first. So our secretary position has a restriction on it. It has to be a male position, so I'm going to list it first. There are 3 viable options for our secretarial position. Then I'm going to look at the president position. The only stipulation that we have on the president is that it can't be whoever the secretary is. So instead of having 5 choices, I'm only going to have 4 choices. Because if David is secretary, he's no longer an option for the president. If Bill is secretary, he's no longer optional. Same thing with Alan. That's why we're going to list the most restrictive restriction. We're going to list the restriction first, and then we look at the next one, because that restriction affects who's eligible for president, how many choices we have left. Because Kathy and Evelyn have no option of being secretary. So it would only be 12 ways or 12 possibilities for us to pair up the secretary and president in such a way within this group that the secretary is a man and the president is not whomever we just stated was the secretary. With 12 options, it wouldn't be hard for us to list all those ways. But as I told you in just a few minutes, we're going to have much larger possibilities, and we're not going to want to have to list them. All right, let's go back and do a number problem. How many non-repeating odd 3-digit numbers are there? This is a lot bigger than thinking about numbers between 10 and 99. We're thinking about numbers between 100 and 999. And then we have this stipulation that they have to be odd. This tells me that the third digit of my 3-digit number has to be a 1, a 3, a 5, a 7, or a 9. It can't be any of the other numbers. It has to be one of these 5 in order to be considered an odd number. So I'm actually going to look at my third digit first because that's where my restriction is. My restriction's on the third digit. My third digit has to be odd, so I have 1, 2, 3, 4, 5 options for my third digit. And then you can look at either your first or your second digit next. It really doesn't matter in this case. I think the first digit's a little bit easier because there's 2 stipulations kind of that we're going to have. What's the first stipulation on our first digit? In order for it to be a 3-digit number, what number can we not include? It can't be 0. So right now we're looking at the numbers 1 through 9. But if we have to have non-repeating numbers, then that tells me, and this is something that you have to, non-repeating means like 1, 1, 1 again. Like we have no repeating digits at all. So there's not another 1 in here. So if my third number is number 1, I can't have a 1 anywhere else in this problem, in my number. That's what it's stating. So if I can't have the number 0 or the number 1, like if it's an example with 1, how many options do I have here?
4. 9,
right? So if I take away 0, I have 9 options.
8.
It's going to be 8. Because if this number is 1, then I can't have 1 here. When this number is 3, I can't have a 3 here. When this number is 5, I can't have a 5 here. Bless you. I don't have to eliminate out all the choices because only one of them is going to be a play at a time. It's very much like we did on the previous problem with the 2-digit numbers. I didn't have to eliminate all of the numbers. I just had to eliminate the one that was going to be affected at that moment. So there's going to be 8 possibilities here. And this one for our second is very similar. I can't have whatever the first digit is or what the third digit is because I can't have any repeating numbers. So whatever the first digit is, that eliminates 1 from my 10. Whatever the third digit is, that eliminates 1 from my 10, leaving me again with 8. So in order to find the total number of 3-digit numbers that have no repeating digits, I would take 5 times 8 times 8, telling me that there are 320 3-digit numbers with no repeating digits. I don't know about you, I'm glad I don't have to write out all those. So the concept of taking away something based on what's already there, sometimes it's easiest to look at one example and work through it. Sometimes it's just going to take some practice. All right, let's do a license plate problem, because this is actually how license plates, why certain states have their license plates arranged in certain ways. If you've ever noticed, California has, 7? I think they have 7 numbers or letters. They have a much bigger population than the state of Missouri, where we only have to have 6. And so we have 3 numbers and 3 letters, depending on how it's arranged. It says, in some states, auto license plates contain 3 letters of the English alphabet, followed by 3 digits. So this one's not Missouri. This one's considering we have 3 letters, 3 numbers. How many such license plates are possible, assuming that there's no other restrictions? Every letter is available, which is not always the case, but every letter is available, and all of our numbers are available. So the way this license plate works is we're going to have a letter, a letter, a letter, and then we have a number, and a number. And it says English alphabet. So first we have to know how many letters are in the English alphabet. Based on previous tests, I know some of you don't know this. So, or at least you don't know how many vowels or consonants, depending on how it was worded. How many letters are in the English alphabet? 26. Yes, there are 26 letters in the English alphabet. And if there are no restrictions, then how many choices do we have for our first letter? 26. And how many do we have for our second letter? 26. That's right. We get 26 options for each of these because there's no restrictions. It doesn't say they can't repeat. It doesn't say the letter 0 is not in there or anything. We can have all the letters. So then how many numbers are possible? Again, it will be 10. Not because the number 10 itself is one of the options, but because 0 is an option. So you have the numbers 1 through 9, and then the number 0, which gives you 10 possibilities. So if I want to know how many possible license plates that there are, I'm going to take 26 times 26 times 10 times 10 times 10. I get 17,576,000 possible plates. That's a lot of dang plates. And I am so incredibly grateful that we have this fundamental counting principle so that we can find out the number of plate options without having to list out all of the possible plate options. Now, obviously, if it was a real state, not all of these would be available. States are always going through and picking out the ones where naughty words are made, and most states have a limitation that either 0 is a possibility or the number or the letter O, but not both, because that gets confusing. It depends on your state. Or sometimes they put a slash through one of them to make it more noticeable. But yeah, the 17 million possibilities, so quite a few. All of this stuff, the fundamental counting principle, is why there's so many restrictions now on digital passwords. I just had to reset mine at Missouri Southern a couple days ago, and it's why you have to use a capital letter and a lowercase letter and a whole bunch of numbers and a symbol, because every single spot then you have so many more options, and so then you multiply them together and it becomes this massive amount of options that makes it less likely that you're going to get hacked. And that's why they don't like repeated things and all that kind of stuff. All right, let's do some more number problems. We're going to do a 4-digit number. It's to be constructed using only the digits 1, 2, and 3. How many such numbers are possible? So in this case, we don't have any restrictions. It doesn't tell us they can't repeat. Obviously, we're going to have something repeat at some point because we only have 3 viable numbers, but we're going to have 4 digits. So we have our first digit, our second digit, third, and fourth. How many possible choices do we have for our first digit? 3. What about our second? 3. Third? There we go. We stay in a pattern. Since there's no restrictions, 3 options are viable for all of them. I can have the number 1, 1, 1, 1. That's totally okay. This is 3 to the 4th power, which is 81 numbers. So there's 81 different 4-digit numbers made up of just the digits 1, 2, and 3. Part B is going to put a restriction. Part B says how many of these numbers are odd and how many of these numbers are less than 2,000. We have 2 different restrictions. So we have to remember we're not dealing with every number that's a 4-digit number. We're dealing with digits 1, 2, and 3. So if we are odd, this tells me that my 4th digit is either a 1 or a 3. It cannot be a 2 because I have to be odd. If I'm less than 2,000, what does that tell us? The first number has to be 1. Exactly. And so I'm going to list my first digit first because it's the most restrictive. It doesn't really matter because it's all in order and there's no other restrictions. It doesn't say that if you are a 1 here, you can't be a 1 anywhere else. So nothing is affecting anything else in this case. But my first digit has to only have one choice. That's not 1 because it has to be a 1. There's just one choice. So there's one choice for the first digit. For the 4th digit, we only have 2 choices. For the 3rd digit and the 2nd digit, sorry, those are out of order. I don't know, I just wrote them that way. We still have 3 choices for each of these. Really, the order that you list these, it doesn't totally matter. With our election problem, it mattered because if David was elected secretary, he couldn't be president. So whoever was elected secretary had an effect on the presidency. This one, it doesn't matter. You could list them 1st, 2nd, 3rd, and 4th. It's still going to multiply out the same. I only have 1 option for my first term. I have 2 options for my 4th term. And I have 3 options each for my 2nd and 3rd digits. 1 times 2 times 3 times 3 tells me there's 18 numbers. There's 18 odd 4-digit numbers that are less than 2,000. It's actually not as many as I would have thought. It's quite a bit smaller. Again, made up of just the digits 1, 2, and 3. That's why it's so small. Are there questions on any of these that we've done so far? We're going to do a couple more, and then we're going to learn about factorials and a couple other things. Because factorials help us with these two. All right, let's flip over. Let's do a golf one. It says Vern has 4 antique golf clubs that he wants to give to his 3 sons, Mark, Chris, and Scott. How many ways can the clubs be distributed? So he has 4 clubs. So I'm going to say club 1, club 2, club 3, club 4. And in this first part, they can go to any of the sons, Mark, Chris, or Scott. So how many different choices do we have for club 1?
3.
Yeah, because they can go to any of them. And for club 2? 3. Right. And for all of them, we have 3 different choices. It doesn't state that all the clubs can't go to Mark. It doesn't say that Mark can only have 1 club and Scott has to have 2. It doesn't have any limitation. So there's always 3 options for who can receive the club. So again, we've already done 3 to the 4th. We did that on a previous problem. It's 81 possibilities or 81 ways that Vern could distribute his golf clubs. Now in part B, we're going to have some limitations. He's going to give specific clubs to specific kids. It says, how many choices are there if the power driver must go to Mark, and the number 3 wood, I know nothing about golf, guys, but the number 3 wood has to go to either Chris or Scott. Those are the 2 limitations that we know. So he's actually named 2 of the clubs. The other clubs, we have no idea what they are. So the power driver has to go to Mark. So there's one option for that power driver. It has to go to Mark. For the number 3 wood, it can go to either Chris or Scott. So how many choices do we have for that club? 2. And then we still have 2 other clubs. I'm just going to call them club number 3 and club number 4. Because I don't know what they are. And I don't know any other kinds of golf clubs, to be quite honest. So I can't just make it up. So it doesn't say that Mark can't have any others, and it doesn't say that Chris or Scott can't have anything else or where they have to go. So how many options do we have for this club 3? And what about club 4? Right. The only limitations were on the power driver, which only has 1 choice, and the 3 wood only has 2 choices. So 1 times 2 times 3 times 3, we have 18 different ways that we can distribute, or Vern can distribute, his clubs based on these different limitations. I know it did. I noticed that whenever I made them up too. And that's just how it worked out, because again, with our last one with our numbers, we had a single choice and then a double choice and then 3 and 3. And so that's why it worked out. Had he had 5 clubs and 3 sons, then we would have had different numbers. But Mark only had 3. Or Vern only had 3. Any questions on that? Yes?
Why is it that on the first one you do 3 to 4 power, and then on the next one you just do 1 times 2 times 3?
You could do 1 times 2 times 3 to the second power. That's fine. It doesn't change anything. It's just less to type into your calculator if you type in 3 to the 4th instead of 3 times 3 times 3 times 3. So it doesn't change anything. It's really your preference. In my handwritten, I show both. So it's totally up to you. Other questions or clarification? Yes?
So I was in your last class, and you said we can't do this with the previous assignment, correct?
You can, as long as you can verify that you have that uniformity. That criteria, the very first one. Because that first problem is actually from our last section. It's from 10.1. And since it has uniformity, we're able to use this fundamental counting principle. But we have to verify the uniformity first. Not every problem from 10.1 had uniformity. And so you just have to be careful and make sure that you're understanding exactly what it's asking for. And as long as there's always the same number of possibilities in every category, then you can do this. Otherwise, you'll have to list. But even with the listing, I think the largest thing I had to list was the number of dice rolls, which is 36 options. And we did that one in class so that you would have that to go back on and look at instead of having to redo the dice roll every time. All right, let's do factorials because this is going to simplify and shorten our lives a little bit. Has anybody ever done factorials in a previous math class, maybe in high school or anything? Factorials are, okay, got one. Factorials are really actually, they're pretty. You can do a lot of art with factorials. I will pull up an image. Sorry, if you're watching the video, you won't be able to see it, but I'll pull up an image at the end of class if you remind me to. And they're very pretty. You can do a lot of really cool things with them. But what a factorial does is if you have n to the factorial, then you're going to take n times n minus 1 times n minus 2, blah, 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 times 2 times 1. You take it all the way down. And so I wrote out a whole bunch of examples, and I think seeing it written out will help. 3 to the factorial means we take 3 times 2 times 1. You start with whatever the number is, and then you go down by ones until you hit 1. So 3 factorial is the same thing as 6. That's what being a factorial means. But writing 3 with an exclamation mark, which is our symbol for factorial, is a lot shorter and more condensed and nicer than writing 3 times 2 times 1. For 6, it's 6 times 5 times 4 times 3 times 2 times 1. So you see that this gets really big pretty quickly. This is 720. Now, before you're like, oh, I don't have to do that, I don't have to multiply this all out. Your calculators do factorials. And I had to find it on this one. On your blue and white one, it's like right there. It's noticeable. But on here, where was it? Probability. Okay. So if you have a calculator like this, like a TI-30 XIIS, there's a PRB right here. It stands for probability. If you click that, you get a menu of these different things, and the third thing over there is the factorial. So 6 probability, go over, hit enter. Now I have 6 factorial, and that gives me 720. So you don't have to sit there and do 6 times 5 times 4 times 3 times blah, blah, blah. You just have to find your factorial button. And if you don't know where your factorial button is, I can show you at the end of class if you have a different calculator. There is a rule where 0 to the factorial is just 1. It's one of those understood rules. So if you encounter that anywhere, make sure you have that. We're going to encounter it here in our set of problems. But I am going to show you some different things to simplify your factorials before we actually do them. We won't always be able to simplify them, and honestly, knowing most of you, you're going to just type all this stuff into your calculator. But I do want to show you that there's some special little things you can do to simplify by hand so that you're not totally dependent on your calculator. Because multiplying 6 times 5 times 4 times 3 times 2 times 1, while it may take you a minute, I hope most of you can do that in your head if you did 6 times 5, and then you kept multiplying it just one piece at a time. We could get to 720. That's not obscene. It's not horrible. The main reason why is because if you forget your calculator on the final day, and this nice pink one is already gone, there is no factorial button on this big old honkin', tax calculator. So what are you going to do? You're going to have to do it by hand, or you're going to have to at least keep track of things. And if you deal with bigger factorials, or when we start dividing with factorials, you're not going to have to do that on an old school calculator or by hand. So I'm going to show you a couple of things to do, because I do most of mine actually by hand, and I rely on my calculator when I have to. Like for the big ones, like 15 factorial. I definitely rely on a calculator for that. So for 6 minus 3 inside of our parentheses with the factorial on the outside, order of operations still holds. I have to do 6 minus 3 first. So that gives me 3, and so it's going to be 3 factorial. We already found that 3 factorial is 6. So we still do the order of operations. Now, when I have 6 factorial minus 3 factorial, that's totally different. Because we've seen on B, 6 factorial is 720. 3 factorial is 6. So I'm taking 720 minus 6. That's 714. These are very, very different. So parentheses matter. Where our factorial is matters a lot. For E, this is one where, yes, you can use your calculator. You could take 720 and divide it by 6. But I'm going to show you how you can expand the top factorial and do an elimination. Because remember, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. It's this whole thing. 3 factorial is 3 times 2 times 1. Notice they have those in common. So you can split larger factorials, 6 times 5 times 4, and then you get 3 factorial. And all of that's over 3 factorial to where your factorials go away. And all I'm doing is taking 6 times 5 times 4, which is 120. This is nice to know in case you lose your calculator or your calculator dies or whatever. Being able to eliminate out like that is a really good process. I don't know what class I learned it in. That's always how I learned to do these. And so I almost always will choose to do that, where I will drag out the bigger factorial until I'm able to cancel out one of the bottom factorials, or maybe it's on the top, whichever, before I actually do my multiplication. Your calculators can handle this. They can do it. Let's see, 6 probability divided by 3. Nope, probability. And it will give you the 120. It does work. Honestly, I don't know if I just did any more work or spent any more time typing it into the calculator than I did if I do the canceling. But it is nice to see this, and if you look at any of my work, I almost always end up doing this. Now this, again, is going to be different than 6 divided by 3 factorial, because we're going to do the division first, in this case, giving me 2 factorial. 2 factorial is 2 times 1, which is just 2. Parentheses matter. All right, in G, we have 4 minus 4 inside of our parentheses factorial. That's 0 factorial, which is 0. No, it's not. What am I doing? It's 1. I said 0, and I wrote 0, and I meant 1, because that's our rule. That's our definition of the 0 factorial. This is a definition. All right, 15 factorial is ginormous, because it's 15 times 14 times 13, blah, 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 blah. And if you type that into your calculator, depending on your calculator, you may get something that looks like this, where it tells you it's 1.3 blah, 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 times 10 to the 12th power. Or maybe yours actually can compute it. I don't know if the blue-white ones can compute it, if it has enough screen space to actually show it. None of your homeworks go quite that large. Every homework problem that you have will be something that you can type in, something that your calculator will be able to produce. But if you get an answer like that, you're more than welcome to write it down. I won't put one quite that large on the final. 1.307674368 times 10 to the 12th power. Nice big old honkin' number. Gets large very quickly.
Is it actually 1 point that many, or is it like?
Yeah, because what ends up happening is this is times 10 to the 12th power, so we'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we'd go 10, 11, 12. So it's a massive number. It would be, let's see, that's thousands, millions, billions, trillion. 1,370,674,368,000. It's quite big. So your calculators will do it, but they're going to give it to you in scientific notation because they don't have enough digits to go across. Or maybe they do. This TI-30 that I have up here will not. So why is that important? Because we're going to do some different arrangements with factorials. So arrangements of distinct objects. This is the total number of different ways to arrange in distinct objects. It's in factorial. So if I had you all stand up, let's say there's 10 of you in here. I don't know how many there are. If there's 10 of you in this classroom and I wanted to line you up here in the front of the class, and I wanted to figure out how many different ways I could do that. Well, there would be 10 choices for this first spot. The first person in line, there would be 10 different options. After that's been selected, obviously whoever's in first can't then be in second. So then there would be 9 different options for whoever's standing second in line. There would be 8 different options for whoever's standing third in line. They can't be these previous people, and so on and so forth. That's why factorials work. And it's also why they get really big really quick. So Michelle has 7 essays to include in her English folder. How many different orders can she arrange them? 7 doesn't sound too ginormous. But when we think about 7 being 7 for the first essay, and then there's 6 options for the second, and 5 options for the third, and so on and so forth, 7 factorial is 5,040 different ways she can arrange her essays. 5,000 ways. Just with 7 items. That's pretty massive. And that's why factorials are nice, because they allow us to see the enormity of the different ways we can do organization without actually having to sit there and list them all. I think we could spend a week's worth of classes just on listing all the different ways she could do it, and we wouldn't get through them, even if all of us took different starters. So this one I thought was really interesting. It says, Trisha's taking 13 preschoolers to the park. How many different ways can the children line up in single file in order to board the van to leave to the park? You wouldn't think, just in general, if you're lining up preschoolers, that it would be this huge number. But 13 factorial is 6,227,020,800 ways. So we didn't even double the factorial in terms of it's not 7 to 14, but look at how big of a difference it made. We went from 5,000 to 6 billion different ways. That's pretty crazy. So these didn't have any stipulations on them. Any kid could be first. Any paper could be first. But what happens if we're looking at things that have lookalikes or things that are similar? Well, then we're going to have this little formula that's going to help us determine the number of arrangements of objects. Because each of these were distinct Each person was different, and it didn't matter the order. But for these other ones, these are going to be looking at the different arrangements of letters within a word, and they're going to have repeated letters. So the number of distinguishable arrangements of in objects, that means kind of unique, different, where one or more of the subsets consists of lookalikes, aka we have repeated letters, that's where we're going to see this pop up, then we're going to use this formula. And this formula looks weird. But what we're going to do is we're going to have this n factorial. N is going to be the number of letters. And I keep saying the number of letters because we're not going to use this formula outside of anything else except for dealing with how to arrange letters within words. That's the only kind of problem we're going to encounter in this class for it. So n is the number of letters. And then these down here, the N1, N2, all the way to NK, these are going to be the number of times the letters come up specifically. And that may not help at all, but I think when you see us work one, it's going to make sense. So N itself, without a subscript, is the total number of letters within a given word. And then we're going to break down that word into its distinct letters. So let's look at the word attract. Okay? Attract has A, T, R, and C. These are the different unique letters. T is in there 3 times, A is in there twice. But if we're looking at unique letters, we have A's, we have T's, we have R's, and we have C's. These are the unique ones. We have 2 A's, we have 3 T's, we have 1 R, and we have 1 C. In total, 1, 2, 3, 4, 5, 6, 7. Or you can add up what you just listed. So there's a total number of 7 letters, not distinct, but just 7 letters in this word. So we're going to use this arrangement of n objects little formula to figure out how many different ways could I arrange my A, my T, my R, and my C to come up with new words. Not necessarily words, because not everything's going to spell something, but I think you understand what I'm getting at. So using this formula, I will take 7 factorial on top, because that's the total number of letters in attract. And then at the bottom, I'm going to put each of my other factorials based on the number of times the letter popped up. So A is going to be 2 factorial. T is going to be 3 factorial. R is 1 factorial. And C is 1 factorial. You'll learn quickly that 1 factorial is 1 and you don't really have to list them if you want to save yourself some headache. How many times do they come up? And you're going to put that to the factorial. So I'm taking 7 factorial really divided by 2 factorial times 3 factorial. And if I do that, I find out that there's 420 different ways we can rearrange these letters and make a distinguishable arrangement, a unique arrangement, even though we have duplicate letters. Try and keep that one separate from niggling. I don't know where they get their words, but they're very neat. Okay, we're going to do the same thing for B. Niggling has N's, I's, G's, and L's. And then it has an I, N, G again, which we already covered. There are 2 N's, 2 I's, 3 G's, 1 L. Total number of letters is what? 8. 2 plus 2 is 4. 3 plus 1 is 4, so that's 8. So this one on top will have 8 factorial. But then on bottom, you'll have 2 factorial, 3 factorial, sorry, I went out of order, 2 factorial, and then 1, or 1 factorial, however you want to think about it. I usually, after the first 2 problems, I start leaving the letters that only have 1 off, because they're not going to affect anything. Multiplying by 1 doesn't change it. So here we have 1,680 different ways we can get distinguishable arrangements within these letters.